I've seen, and you can find books where I'm the editor of a bunch of submitted papers on election technology and so on. Generally, there's what we call the election administrator, as we refer to them euphemistically as the EA. And so generally, everyone sort of has to trust them, maybe not to spy on how people vote or other things. And so one of the challenges that, not the key one here, but that VoteXX also addresses, not shown here, is it's totally decentralizable. So we can make it so you'd have to compromise, like, it's like BFT or whatever, almost all the nodes in order to spy on people or mess with things. Now, it's not as big a deal as maybe I might be giving the impression, because theoretically, these cryptographic protocols allow us to ensure that the count is correct, even if some of the EA tries to cheat. But then the EA can kind of see who voted which way, or you can kind of flip it. But anyways, to have a system where there is no EA and it's totally distributed, I believe that's pretty much unique, and that's what we really need for our governance. So that was, that and one person, one vote, as opposed to buyable votes. Those are the two things that we uniquely need for our governance, and we've been saying we could do, and now VoteXX is proving it's quite doable. Go ahead, Mario. Yeah.
Absolutely, yeah. So, just the key ideas that so that people can actually understand this better. So the key idea is that we're going to use a mixed network, right? So it makes perfect sense that we take advantage of using a mixed network, since that's a big part of our company. So as much as we can use of CMix, it would be ideal to use. So you're going to easily see how that's done. Then we have this notion of a hedgehog. So voters should be able to share their secrets with a hedgehog. So basically, a very simple example could be David can instantiate me as a hedgehog. So David can be like, Mario, if anyone tries to buy my vote, I'm going to just play it safe and give you some key material so that you can then cancel a vote on my behalf. And you can instantiate many. So I can be like, you know what? I'm going to trust Bernie to cancel my vote. I'm going to trust Balthazar to cancel my vote. I'm going to distribute it between multiple people that I know that are going to get the job done. So that
I would like to say this is a unique notion. It's never been
exactly, yeah.
This is and since the hedgehog is Mario's favorite critter, we have all these entities hedgehogs. Okay.
Yeah. So basically, the hedgehog is just it's an entity with secret key material, and that entity is able to change or actually cancel the vote. So just a quick note here that we mentioned that we're robust against a strong coercer. So even if this person trying to buy your vote learns literally all the secrets from the voter, then you're still able to actually change or cancel your vote. So let's just go over exactly how it works. So first we have a registration stage.
Here's the results
as far as I know, this applies mostly to the US setting. At least for us Europeans, we're automatically registered, but there's we assume a registration stage to be as modular as possible. So here, users are going to actually register 2 voting public keys. In these examples, we always assume that you vote either yes or no, or participant A or B. So we can, for simplicity, we can just think Trump and Biden. So that would be public key 1, public key 2, right? So that's the registration stage. Then voting stage, you're going to cast your vote. So you're going to sign with the corresponding key, right? You have a key for Biden. So you just sign a message with that key, and you're automatically voting for Biden. And then we have a nullify stage, where you're actually going to nullify your vote.
Where a hedgehog can do it
exactly.
Yeah. It's not usual, but in case someone coerces you, or you decide to sell your vote in order to harm the other side, then they will never know that you've got hedgehogs nullifying your vote.
Yeah, exactly. So here we're just going to show how the registration works. So people are going to submit their encrypted public keys. There is an entity here. You can look at this as the government that allows you to register or not. And then this stuff goes over CMix, right? So the keys then come out unpermuted. So you know who registered, but you don't know to who like each key belongs to. So you know which keys are valid and which keys belong to valid voters, but you cannot really map one specific pair of keys to like Mario, Baltazar, David. Like you just know the actual, what we call a roster, like all the list of valid public keys. So
I'd like to just, without interrupting your flow here, just point out that a system like this is perfect for sample voting. You could do sample voting automatically in it. You just pick some of those keys in the middle and say, okay, great, these are going to be voting on this, and those ones will be voting on that, and yeah. Okay.
Yeah, absolutely. This is a very good example. So you can have like a full list, let's say with 1 million people, and then you can sample like 10,000 to vote on like a specific referendum, and then you can sample a different 10,000 to vote on something. So it's very practical for sample voting. It's a big plus here. So voting is extremely simple. So like the step one, you're just going to construct your vote. So like I was saying, you're just going to sign a message with the corresponding key, and then you're just going to submit your encrypted vote. So here you see like user 1 submits his vote 1, is voting for yes, and user N submits his vote for no. Stuff goes over CMIX, comes out unpermuted. So here,
this could be just over our network.
Exactly, yeah.
It doesn't have to be in special batches or
anything. This is just normal message.
CMIX.
Oh, the running over Arrow SDK, for example. Yeah. A quick.
Beautiful thing.
And now we introduce this notion of an initial tally. So we have an output with permuted votes. So you know how many votes correspond to each outcome, but you don't really know which person voted which way, right? But you imagine I'm user 1. I can check that my vote is here, right? Because I submitted the encrypted thing. I can check that the output is correct, but no one actually knows that Mario voted for yes. So we have this notion of verifiability. I cast my vote. Stuff went encrypted, but I can check that it made it correctly to the other side, and it's on the initial tally. Why is this an initial tally? Because now we're going to have this third stage where the hedgehogs are actually going to be trying to changing or canceling the votes. So we have this temporary tally, and then we have this, we're now going to go over the nullify stage. This is a black box overview because just to show the basic idea, because then the actual protocol is quite a significant thing, but
you're going to show it, right, Mario?
Yeah, I am. I'm going to show it. Yeah.
Not explaining in detail.
No,
maybe a little more of a lunch and learn than.
Yeah, that's
good. That's good. Go ahead.
So this is just the overview, right? So basically, what is happening in this nullify stage? We're going to have voters or the hedgehogs. They're going to interact with the mixed nodes to change or nullify their vote. So we're representing here that a voter 1, this little hedgehog in red, and the voter N are actually going to try to change 2 votes, 1 each. To do so, we have as outputs the list of cast votes. So in that voting stage, we saw all the signatures coming out. We're literally going to grab all of those signatures and we're going to plug it into a mixed cascade. Then these hedgehogs are going to show us a proof of knowledge of a secret key, and so they're basically going to say, I know a secret key that allows me to change a yes vote. That essentially that's the statement that is happening here. So they're going to interact with the mixed nodes, and they say, I know a secret key that corresponds to a yes vote, and I would like to change that. And then that's what's going to happen here. So we're going to have a nullify results, and you're going to be able to see okay, we're going to subtract 2 yes votes and change them to 2 no votes. So we had that initial tally before, and then we apply this transform and we get the actual final election result. We're now going to show a very concrete detailed diagram of how this works.
Can I just, while you're amazing people with this, okay, there will be a quiz. No, but the thing is, it's almost like quantum physics because, if you were to show all of your keys to the vote buyer, he, let's say, would never be able to find out that you already gave your keys to the hedgehog and that the vote ends up being canceled through this protocol. That's hidden from the vote buyer. See, this is the big problem. If someone says, I'll buy your vote, and you say, great, I'll give you my keys, you can watch me voting, whatever, and then later they find out that you cheated them, they might do something really mean to you. So this is why we don't want anyone to know about that. And so through this mechanism of the hedgehog, which is very hard to know or find out about it, because you could have at any point, but even before the election, got this hedgehog set up, then the vote canceling act is undetectable, even if all your keys are known to the vote buyer. They can go and say, oh, I'm a hedgehog, I'm trying to cancel this vote, but they won't even be able to find out whether there's another hedgehog who canceled the same vote or not. That's part of what all this fancy stuff achieves.
Yeah, we actually have like I'm not going to spend a lot of time on this, but we actually have like 20-something slides where we actually have a little animation that goes over.
Our lunch has gone about as far.
Yeah, exactly.
We just want to impress you.
Just to show the main idea, yeah, like the votes come in here, and then a lot of transforms take place in like each of the mixed cascades. But then in the end, you're actually going to be able to look at the parity in a private manner, and you're going to be able to see like, oh, okay, we can subtract 2 yes votes, and we're going to be able to add 2 no votes. This took a while. This took a lot of effort, and this is why this is version 3.0. And so far, it seems to be pretty unanimous among the entire working group that this is a solid working solution with pretty decent scalability and something that has never been seen before. Even Jeremy is very big in the election space. He said that usually there's 3 ways to approach this whole like vote buying problem, and then like now we're introducing a 4th way. This like
the interesting thing is that the second and third way people are starting to write articles that they don't even believe in the second and third way anymore. Exactly. There's a collapse in the anti-vote selling theory. There are people who write about this subject more from a philosophical and ontological, and more from a technical and cryptographic points of view, and it's all kind of cratering. And so this is a completely different approach, which just, I think, knocks the ball out of the park. But part of the trick, the weirdness, is that the underlying system reveals pretty easily how you voted. But then we have this canceling thing, but you can't tell who's canceling. That's the difference. And so it makes it really suitable for sample voting, and it seems to be as general as is theoretically possible, and it does really hang together, and it fits in a fully decentralized digital world, which previous schemes have not. So this is what we need. It's perfect for what we need. So, and Mario, can I just take the floor back and wrap this up real quick, because we've been, last call was pretty short. This was